Okay, lesson section 2.1, limits and continuity. The first thing we're going to talk about before we talk about limits or continuity is the definition of average rate of change. You're going to see this a lot in this course. You're going to see find the average speed, find the average velocity, find the average acceleration. Anytime you're asked to find an average rate, you're going to take the slope of the secant of the function. So let me draw you a little picture here, and I think at this point we've probably already seen this and talked about it, but I'm going to draw it again anyway because really quickly I want to explain this whole t plus h thing because I think it's pretty confusing when you just see it in that notation. But here's what it looks like. This is just a function, okay? In order to find the average rate of change between these 2 points, we're going to find the slope of the secant line. This point right here is f of t. Remember, the point has a y value. When x is t, the y value here is f of t. You have to remember that f of something is really a y value. Now, we're going to say that the function keeps moving along for h number of minutes, seconds, hours, whatever amount of time we're talking about. And its new position here is t plus h. That's how much time has gone by. After h seconds, this x value is now t plus h. Well, what does that make this y value? It makes this y value f of t plus h. So that's where the slope comes in. If you think about doing y minus y over x minus x, this value is f of t plus h. This value is f of t all over h, which is the change in x. So that's where the formula comes from. I like to do that. That's where this handy dandy little formula comes in. Change in y over change in x gives you your average rate of change. So for instance, an object dropped from rest falls at y equals 16t squared feet in t seconds. Find the average speed during the first 3 seconds. So h in this case is 3 because that's how much time has elapsed. It dropped from rest, which means that t equals 0 to start with. So if t is 0 and h is 3, then we're going to find f of 3 minus f of 0 all divided by 3. And when you do that, you get 48 feet per second. On the next one, we're going to talk about instantaneous rate of change. So we were talking about the average amount it changed over a period of time. Now we're going to say at this given moment in time, what is the speed of the particle? And so think about at a given second, what's the elapsed time? How much time has passed at a given moment in time? Hopefully you recognize that h would be 0 in this case. There is no elapsed time at a given second. So this is where we have to use limits to start evaluating things. If h is 0.00001, it's not 0, so it's not undefined, but it's really small. So we're going to do this problem and find the instantaneous rate of change at t equals 2. Before we can do that, however, we should talk about what happens when h gets really, really small. And I had a nice box in here, I don't know where it went, covering all this up so you don't have to look at it yet. I don't want you to get confused. Don't look at that. Look at this. This is doing this problem, finding the instantaneous rate of change at t equals 2, using a whole bunch of different values for h. And you should notice that these are getting smaller and smaller and smaller and smaller and smaller, otherwise known as closer and closer and closer and closer to 0. Because we can't use 0 because this would be undefined, but we want to get really, really, really close to 0. So what this person did is they plugged in 1 for h and evaluated. Then they plugged in 0.1. I think you should do this on your calculator. You should try these calculations so that you can see where these numbers came from. But you notice that as h gets closer and closer and closer and closer to 0, the average speed gets closer and closer and closer to 64, which means that at the instant where t equals 2 and h is 0, the speed of the particle is 64 feet per second. So if we were to evaluate this algebraically without doing all this work to figure out that it gets to 64, we would simply leave in the variable h and we would see what happens. I will tell you that what's going to happen every single time you do this is the h's are going to cancel out, and there's going to be somewhere that you can plug in 0 for h that won't be undefined. But let's talk about the algebra here. When you square a binomial, you get a trinomial. If you don't believe me, write it out and FOIL it. 2 times 2, 2 times h, 2 times h, h times h. You get this crazy trinomial here. and then this function, this value is 64. So then distribute, combine like terms, do all your algebra, you end up with this expression, which has a GCF of h. So you take out the h's cancel out, and you're left with this expression, 64 plus 16h, which when you plug in h being 0, you get the average, or the instantaneous rate of change is 64, just like it was here. So just to review, to do this algebraically, you use the formula, f of t plus h minus f of t all over h, do some algebra, get it so that h's cancel out, and then plug in 0 for h. Okay. Woo! This is a limit. The definition of limit is the limit as x approaches c of a function equals a number, which is a big L, just limit. So in the last problem, we would say the limit as h approaches 0, as it gets really small, of the function is 64, and it should say feet per second. Here's another example. Sometimes when you try to take a limit algebraically, you end up with 0 over 0, because the sign of 0, hopefully you've memorized that, is 0, and 0 for x would be 0 over 0. This is called indeterminate. We can't just leave it like this. We have to investigate it further and see if we can figure out if the limit is really, we know the value of the function at 0 is indeterminate or undefined, but do we know what the limit is as x gets really close to 0? Well, we can look at the graph, and it looks like as x gets really close to 0, the function takes on values of 1 on either side. But let's investigate a little bit further. Let's go to the calculator. Sorry for the random pauses to breathe, but hey, it happens. Okay, so I'm going to need that, no, not. So make sure we're in radian mode. Sine of x divided by x, and we're going to look at the graph. Now it looks like it gets close to 1. It actually looks like it equals 1, but it can't equal 1. So then we go to the table and we investigate. Now I set my table up to change by thousandths. To do that, you go to second table set, and second table set. Your delta table, you can change it to 0.001. That's useful for finding limits because we want to know when something gets really close to a number. And in this case, we want to know when it gets when x gets really close to 0. So I'm going to start my table at 0 so that I can look on either side of it. And as you can see, that to the left of 0, the value of the function is 1, and to the right of 0, the value of the function is 1, even though at the 0, the function is undefined. That still means the limit as x gets closer and closer to 0 is 1 of this function. And this is one you're going to have to memorize. You're going to be getting a list of about 10 or 15 things per semester that you have to have memorized, and this is one of them. So the lesson here is, even though at 0 the function is undefined, the limit is still defined to be 1. The function doesn't have to have a value, but the limit can still exist. Okay, so here we go again. F of 1 here is undefined, has no value because there's a hole. But the limit is still 2, because as you go from the left, you get close to 2, and as you go from the right, you get close to 2. Here, the function has a value at 1, but the value is 1, but the limit is still 2. And here, the limit is 2 because it's continuous. Here's all your limit rules. I think you should write these down. We're going to talk about it a little bit, but there's nothing really crazy important here. Basically, the product rule is going to show up a lot. If you have a limit of a product, you can just take the product of the limits. So let's try some examples. Unfortunately, I already made this video once and it froze, so now I'm not going to rewrite all of these things. Maybe I am. It's only helpful to you if I do all the work. So the first one we're going to talk about is the limit as x approaches 2 of 3x. The limit as x approaches 2 of 3x. Think about what the function 3x looks like. It's a line, right? And if you travel along the line, as x gets closer and closer to 2, what is 3x approaching? Well, it's approaching 6. Whenever you have a continuous function, meaning you never have to pick up your pencil, it's continuous everywhere, all you have to do is plug in the number for x to evaluate the limit. It's also worth mentioning now that a limit only exists if the limit from the left-hand side of the graph and the right-hand side of the graph are the same. We're going to talk about that a lot, but you might hear me say the limit exists or the limit doesn't exist or something, and I want you to know where that's coming from. Okay, the next example from our flip chart is this one right here. And this example, again, it's continuous everywhere, so you can just plug in 2 and get your limit. But this is the one I want to use to show you what the sum of the limit thing is all about, that rule about the sum of limits. So we can see that if we put in 2 for x and square it and multiply by 3, this gets you 12. Minus 4 is 8 plus 7. So this limit is 15. But watch what happens if we break it up and say the limit as x approaches 2 of 3x squared plus the limit as x approaches 2 of negative 2x plus the limit as x approaches 2 of 7. So here, 2 squared is 4 times 3, this is 12. Here, 2 times negative 2 is negative 4, this is minus 4. Here you have a constant function of 7, so as x gets closer to 2, y gets closer to 7, and you get the same exact answer. I would never suggest doing it this way. It's just worth showing you that if you ever need to, you can do it this way. This limit of a sum is the sum of the limits. Now this one is where things start to get really hairy. When you plug in 2 here, you get 0 over 0. And we already said when that happens, something weird is going on, and we have to talk about what that is. So let's take a look at the graph, x squared minus 4 over x minus 2. I'm going to do a lot on the graph for the first few units to make sure you get really comfortable, because you have to be able to use this calculator. They don't clear your memory on the exam. They don't care what you have on here, but you have to know how to use it all. And there are a lot of questions where you can't use it, so we'll have to practice those. But in order to investigate these things, I think it's definitely worth showing you how to do it on the calculator. So again, we can look at the graph. It's just going to be a line. And when x is 2, which is what we're approaching, right, you can't really tell anything. It just looks like it should be 4. But if you go to the table and investigate, now again, I want to start, I like it changing by 100 tenths, 100 thousandths, but I want to start at where my limit is so I don't have to scroll. So I'm going to start at 2. And now we're going to look at the table. Now you can see that that function does not have a value at 2. It's undefined. However, immediately to the left of 2, it's starting to look like 4. And immediately to the right of 2, it's starting to look like 4. So the limit as x approaches 2 of this function is 4. Let's prove it algebraically. So what we have to do now is anytime you can, you want to factor. So we're going to factor the top because it's the difference of perfect squares. And then it cancels out with a factor in the bottom. So now the limit as x approaches 2 of x plus 2 is 4. So our answer is 4, which we just proved on the calculator. Okay, next one. Again, you're going to end up with something over 0. Actually, negative 1 cubed is negative 1, minus negative 1 is plus 1, so 0 over 0. So we have to evaluate algebraically. Factor the top, we're going to factor out an x. Now that didn't help us at all because the bottom is still 0. So we have to keep going. And every time you write another step, you're supposed to write the limit as x approaches negative 1 of x. Hopefully you recognize that this is also the difference of perfect squares. And then these cancel. Now we can plug in negative 1. And we get negative 1 times negative 2 is positive 2. Down here, again, we're going to get 0 over 0, because 2 times negative 8 is negative 16, plus 16 is 0 over 0. So we have to simplify. Well, we have a common denominator, so let's write it as one fraction. And let's make sure we write the limit as x approaches negative 8. Now hopefully you realize that you can factor out a 2. These cancel out. So the limit as x approaches negative 8 equals 2. A few more. Oh, geez. Okay. This one is pretty obvious because it's continuous everywhere. There's no fraction or radical, so we just plug in 3 and you get negative 9. This one, I think, no, I guess I didn't mean for it to be negative 2. Again, it's continuous everywhere except negative 2, but around 2 it's continuous, so we can just plug that in and we get 3. This one is where the product rule comes in. If you were to evaluate the tangent of x, tangent of 0 is 0 over 0, so it's indeterminate again. We have to figure out a way to simplify this. And trig functions are hard, but we do know that we were told by our teacher to memorize that the limit as x approaches 0 of sine x over x, we know what that is. So how can we, what can we do to change this so that you can incorporate this into it? Well, hopefully you remember the identity that says the tangent of x equals sine of x over cosine of x. So this part looks like this. And then if you think about it as the tangent of x times 1 over x, these two things are the same. Tangent of x over x is the same as tangent of x times 1 over x. That means I can do sine of x over x times 1 over cosine of x. These expressions are exactly the same. This is why you have to be good at algebra to be able to do calculus, because you have to understand that this is the same as this. And so the product rule says the limit of a product is the product of the limits. So the limit as x approaches 0 of sine of x over x is 1 times cosine of x. Cosine of 0 is 1. So 1 times 1 is 1. Last one. This one's a doozy. So again, you see if you plug in 4, we're going to end up with 0 over 0. So we have to do something to fix that. Now, whenever you have a radical like this, you want to multiply by a conjugate. Remember, the conjugate means you change this sign. So we're going to multiply by the square root of x plus 5 plus 3 over the same thing. Multiplying by 1, so we're not changing anything. So when we multiply the top, this is a binomial times a binomial. And again, I'm going to write the limit as x approaches 4 of a binomial times a binomial. So first, when you multiply a radical by itself, you get the number underneath. The outside and the inside, when you multiply by a conjugate, will always cancel out. That's why we multiply by conjugates, so that the outside and the inside will cancel out. And then the last is negative 3 times 3 is negative 9. On the bottom, I'm not going to do all that multiplication. I'm just going to leave it because I'm hoping something will cancel out. And I'm hoping it's the thing that's making my bottom 0, which is this. But let's see what happens. Square root of x plus 5 plus 3. That's all on the bottom. When you combine like terms on the top, hopefully you realize that you get x minus 4. Over this whole thing. So the x minus 4's cancel out, and when you plug in 4 for x, you get 1 over 5 times 4 plus 5 is 9, square root of 9 is 3, plus 3 is 6, 1 over 30. There you go, all done.